Bet it'll take twice to share this. Absolutely it does, because it always does. It just does not like the Elmo. Okay, so on Wednesday, you have a conceptual checkpoint. And the conceptual checkpoint is this. I'm going to zoom in. Okay. And for those of you in class, I'm going to change up the way my Elmo is for tomorrow. So it's not up on this big box, although it is nice to have somewhere to put my stuff. Okay. So yesterday we looked at how windmills change wind to light. And what we came up with is what's right here on our board. We said the windmill system, hold up, someone just messaged me. I think, maybe not. Okay. We said when wind collides with the blades, energy is transferred to a generator. The motion of the spinning blades moves the magnets inside the generator, where the motion energy transforms into electrical energy. That electrical energy is transferred through the wires to the skateboard. And on the skateboard is that LED light. And that electrical energy is transformed into the light energy. Okay. So the windmill is transforming motion energy into electrical energy and then into light energy. Okay. The electric current transfers electricity through the wires. And of course, the wind is colliding with the blades, transferring energy. Okay. So that's how the windmill harnesses the wind to turn wind energy, which is motion energy, into electrical energy by way of the generator, which then transfers to the wires and turns into light energy to light up the LED light. Okay, so we're going to change that question up a little bit today for this conceptual checkpoint. Conceptual checkpoint gives us this prompt. And remember, on the conceptual checkpoint, you can use everything in your logbook. Okay, so here is the prompt. There's a lot to it. That's why I didn't write it in my notebook. A woman in a neighboring village heard about what William, as in the boy who harnessed the wind, William, did to transform wind energy into electrical energy, which is what we've been talking about since November. She is excited at the idea of using electricity to pump water, just like William did. Develop an explanation for how this woman can use a windmill to turn on a water pump and provide enough water for her family. Apply all of the knowledge from the key concepts checklist. So if you recall, our key concepts that we wrote down yesterday were energy transformations, energy transfers, relationships between energy and speed, and indicators of energy. So we need to make sure we're using all of these concepts in our answer. So I'm letting you see this. I'm very visual. You guys, you know that by now. Those of you who are in my physical class, you've seen my classroom. Those of you who are virtual, all you can see was what's behind me. You can't see what's on my back wall, but my classroom is decorated, believe it or not, thoughtfully, because I'm visual. Okay. Arts, that's my thing. Arts and science, where they merge. I can read things and recall some of it, but if I can see it and read it, I do better. So that's why I have this for you to see. I want you to hear me. Okay. This is a perfect 5 out of 5 answer on the conceptual checkpoint. The woman can use a windmill to turn on a water pump. First, motion energy transfers from the wind to the windmill, making the blades move. Instead of using the words move, you could use the word spin. Okay, either one of those words would be fine. Then the generator transforms. I need to see the word generator, and I need to see the word transforms, and I need to see the words motion energy into electrical energy. Okay, I need to see those words. By producing an electric current. Okay, you might not say electric current, but you could say electrical energy. Next, the current transfers energy through the wires that connect the generator to the pump. That is how wind turns into electricity. When the blades spin faster, they have more energy of motion. This is telling us about this key concept. Relationship between energy and speed. And we've also, without using the word collision, we did talk about wind hitting the windmill. That's a collision. Okay. That is how wind turns into electricity. When the blades spin faster, they have more energy of motion. This means there is more electrical energy being transferred to the pump, which would pump water faster. I know this. This is giving evidence because in the windmill model, the light is brighter when there is more wind. This is giving evidence that we have collected since November. This is giving evidence. Got it? You give me evidence like this. I know this because in the windmill model, the light is brighter when there is more wind, and your dear old teacher might actually give you a bonus point. And you know how hard it is to come by bonus points. And a lot of my students are not doing so great in science right now because your lesson 10 was worth 27 points, and a lot of you did not do so well in lesson 10. There were key concepts such as transform that you did not include, even though your teacher told you to. And so your grade in science is not so great because that was a 27-point assignment. Okay, so if you include this part, I know this because of the windmill model, the light is brighter when there is more wind. That's going to possibly give you a bonus point. Okay, I don't get bonus points very often. Okay, the other thing that's very crucial about this conceptual checkpoint. Thursday, you have your Module 2 assessment. In other words, we're testing out. It's a unit test. Okay, I'm not supposed to get bonus points, but I'm taking this conceptual checkpoint question and I'm putting it at the end of your module assessment as a bonus question. Because, as you guys know by now, when you turn in work, I give you customized feedback and I tell you where you lost every bit of your points. So you will know, especially if you watch this video, exactly what you needed to do to make a perfect score. Okay? So another answer you could give for this that would also score a 5 out of 5 is, I'm trying to get this moved up here. The woman can use a windmill to turn on a water pump. First, wind colliding with the wind. Look where the hyphen goes. I got to zoom out a little bit. See where I use a hyphen. The woman can use a windmill to turn on a water pump. First, wind colliding with the wind. Mill blades would cause the blades to spin. Then that would cause the generator's magnets to spin, creating electrical energy. This electrical energy, that's electrical there, would travel through wires from the generator to a water pump. And this way, a windmill could be used to power, nope, I forgot to use the word transform. Okay, wind colliding with the windmill blades would cause the blades to spin. Then that would cause the generator's magnets to spin, transforming into electrical energy. That's why we use pencil. Transforming into electrical energy. This electrical energy would travel, would transfer, to use our technical scientific terms, transfer through wires from the generator to a water pump. And this way a windmill could be used to power a water pump. The faster not the faster. Okay, the faster the blades spin, the more energy of motion they have. So they would pump water faster. I know this because in the windmill model, the light is brighter when there is more wind. Okay, I'm going to move this so you can see that better. Okay. All right. That's just a little different version. The woman can use a windmill to turn on a water pump. First, water colliding with the windmill blades would cause the blades to spin. Then that would cause the generator's magnets to spin, transforming into electrical energy. This electrical energy would transfer from wires from the generator to a water pump. In this way, a windmill could be used to power a water pump. The faster the blades spin, the more energy of motion they have, so they would pump water faster. I know this because in the windmill model, the light is brighter when there is more wind. If you want to add in there that movement of the blades and the water pump moving are both indicators of energy, be my guest. Okay, but this is already very long. Okay, and this is the crucial information I need you to write. Okay, that's a lot of information. And you're going to have to fit that on page 47. Let me show you what kind of room you have on 47. Okay, it's a whole page, yes, but my students tend to want to write as little as possible. Okay, had a lot of experience with this over last year, this year. Okay, it's a lot of writing you have to do. But again, this is worth 5 points tomorrow, and this is going to be bonus on your test for Thursday. Thursday's test only has 4 questions, but every question has multiple parts. And there's so much critical thinking involved with Thursday's questions. Okay. Now I'm going to leave you alone for a minute or two so you can see this. And there's the question just above that. Okay. Okay, so let's go to the conceptual checkpoint, which is in the very back. It's not the easiest to find, unfortunately. It went too far. I've got to go make a bunch of copies. All right, guys. So I'm going to show you the questions first, and then I'll show you the answers that are given in the book. Okay. There's so many sources scattered about. All right, end of module assessment. Here's your question 1. Imagine you're in the kitchen helping to cook dinner and listening to music. Draw a model to show the indicators of energy that you would observe. Be sure to label your model including the indicators of energy. Okay, so you're going to want to draw a stove, a microwave. Don't you have a light in your kitchen? You might want to draw cabinets. I know for me, I have lights above my cabinet, lights below my cabinet. So I have over cabinet lights and under cabinet lights. I have a stove with burners and an oven. I have a microwave. You might want to draw a coffee pot in there. It says listening to music. So I don't know if you want to put headphones on your little stick person. Okay, that's up to your discretion. Let me show you what they have in the book for theirs. They have a ceiling fan to show motion. They have arrows. They have light coming from the ceiling fan. They have a burner on the stove. This is to show heat, and it says temperature change. They have a stove, and you could even go one further and show, see these little waves out here? My students in my class might recognize that as temperature change. From oven. Okay. And then you need to show me that it's plugged in, because that stove doesn't just get electricity out of the air. Thank goodness, or we'd be getting shocked. This person is walking towards the stove. So these lines are to show motion. Person, motion. Because person is walking. Sound is the radio. And the radio is plugged in. Okay. I would go one further and I would draw cabinets with microwave. And I would label microwave. And I would put temperature change, because inside there is a temperature change. And then I would have to draw another cord for electricity. Okay. That's a very minimal drawing. All right. I personally wouldn't have a ceiling fan. I would have a chandelier for mine, and I would have cabinets all around because it's in a kitchen. All right. So mine would look a little different. It'd be more along the lines of upper cabinets. Then I have wraparound cabinets. I don't know how to do that, but upper cabinets, lower cabinets. Then I have glow lights, I guess you'd call them. They're those lights at the bottom. It's called under cabinet lights. Then I have lighting above my cabinets. I have a lot of lights in my kitchen. and it's rope lights up here. And yes, I have lots of plug-ins in my kitchen. It's custom made. So rope lights. All right, so this plugs in electrical energy. All right, so I'm going to show a plug. Electrical energy over here. I know it's not a square. Oh well, sue me. Not really. Electrical energy. Make it where I can read it, okay, guys? All right, these are lights. You see I'm labeling all this. So these have a plug. And you see I'm labeling all of these electrical energy, okay? In the middle right here, I have my stove, flat stovetop, ceramic stovetop, okay? It's a stove with a pot on it, okay? And I'm gonna put heat, so change in temperature. And the same thing, plug in. So electrical energy. I'm going to draw a line here and here and label these plugs, okay? Because they are. I've got plugs all over my kitchen. Plug, plug. 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 Electrical energy. Okay. Then over here, it's recessed into my cabinet. I have a microwave in here. Okay, so microwave. I'm going to label it. I know it's not the best drawing. Oh well. And I'm going to put, microwaves are invisible, but it's supposed to be temperature change inside the microwave. Actually inside the bowl of water. Temperature change. Okay. So temperature change inside the bowl. This cooking in the microwave. Temperature change on the pot on top of the stove. Okay. Lights that are plugged in. Lights that are plugged in. Lights that are plugged in. I don't have under cabinet lights over here because of stovetop. I'm not really wanting to cook the lights. Glow lights here that are plugged in. They're microwave. It's plugged in. Okay. Then I have a fridge. And it has an ice maker. Ice maker. So that requires energy because it makes things colder. So temperature change. And the refrigerator requires electrical energy. And it goes to a plug. Obviously, I don't have 3 things on a plug because they're not on extension cords. We have lots of plugs, like 18 of them in the kitchen. This is, like I said, specialty built. Okay. And then we have more cabinets here. Let's put that radio in here. Okay. I'm going to go old-fashioned radio. Speaker, speaker. How'd they draw their radio? Sound. Radio. And the radio has to plug in. Oops. Not 3 plug-ins, just 2 plug-ins. And the way we have our outlets, we actually have them on the wall. So that's another plug. We actually have like lots of plugs along our walls. Told you. We have lots of plugs in our kitchen. Okay, electrical energy. Sound. Okay. We're going to have the person, kind of long legs, shorter arms, walking. So person walking. Okay, so that's what I'm putting in parentheses. Motion. Okay. So lights, electrical energy, plugs, lights, stove. So that's change in temperature. Person walking, that's motion. Rope lights, that's electrical energy giving it energy. And the plug, and I had the plug listed. I had the upper cabinets labeled. Upper cabinets labeled over here. Lower cabinets. Lower cabinets again, labeled. Plug. Plug. Lower cabinets, microwave, fridge. Try to spell things right. I'm not playing a guessing game tomorrow. Temperature change, because ice maker. It's also attached to the water. Okay. My sink is over here. I'm going to draw in my sink. It's actually all the way over here. I have a big sink. And I actually have a light here and over here, but I don't want to try to draw on 2 of them. Okay. But my sink is a big one. Okay. That's actually the floor plan loosely of my kitchen. Okay. It answered that question. Helping to cook dinner. My dinner's cooking. Microwave and stove. If you want to draw on the oven, label it oven. And you can also show change in temperature. Because when you're cooking dinner, you could be using the oven, the stove, and the microwave at the same time. Right? And if you're helping cook dinner, you're in the kitchen, hopefully walking, not running, but you're in the kitchen helping cook. And you got the radio, because it says in there, listen to music. Okay. And I'm going to take a wild guess. You're not in the dark. So you have the lights. All right. It's a lot to that. Okay. So I'm going to guess I'll probably put about 8 points on this one question. This is one rendition. That one's my kitchen. Has a person in there. I showed the person is moving. Has the oven, change in temperature. Has a fridge, change in temperature, because my house has a refrigerator. It shows my lights above my cabinet and that they're plugged in. They don't just have energy magically. They're not solar powered lights, because my house has a roof. I have my little under cabinet lights, glow lights, because they're really, really low in wattage. They're really hot though. Have my lower cabinets, have the radio and plugs, because that's where the electrical energy comes from. I have my radio plugged in. I have my microwave plugged in. I have my refrigerator plugged in. I have my sink, because I have to have somewhere to wash my hands. Everybody's in my classroom knows I'm kind of crazy about keeping hands clean. Rope lights plugged in. Stove plugged in. Okay. Everything has to be plugged in if it's an electrical device. You have to show your electrical energy. You have to show your plug. You have to label everything. Okay, guys? All right, that's your number one. Like I said, 8 points, because that's a lot to draw and label. And you have to label sound coming out of the radio. Okay. It shows lights. So obviously lights are putting out light. All right. Your number 2 question. This one can be confusing. We did it in class together, but it was with me really leading. Okay. This one says a pencil, use a pencil or highlighter. You're going to use a pencil to analyze the data set below. Then you're going to answer questions. And it seems like it's not hard, but kind of is. Student A and student B are curious about who can kick a soccer ball into a goal with more energy. This relates back to when I had a student run into a desk versus I had a student walk into a desk. Think about which student brought more energy to the desk. Was it my runner or was it my walker? Which one had more energy that went into the desk? I know in my first block, it was Innocente versus Ali. Innocente ran, Ali walked. The person running brought more energy. Okay, keep that in mind. Okay, student A and student B. They know that a slower ball will take more time to reach the goal. The students take turns kicking the ball from the same location, because remember we have to have fair test, and timing how long it takes for the ball to reach the goal. Their data set is displayed in the table below. So student A, trial 1, 4 seconds, 4.5 seconds, 4 seconds, 4.5 seconds, 5 seconds, 4 seconds, 4.5 seconds, 4.5 seconds, 5.5 seconds, 4.5 seconds. Student B, 6 seconds, 5 seconds, 5.5 seconds, 4 seconds, 5 seconds, 5.5 seconds, 5 seconds, 5 seconds, 5.5, 5. So look at this. A is faster, B is slower. A is faster, B is slower. A is faster, B is slower. A is fast, B is faster. So this one's different. You see that? They're the same here. They're the same on 5. A is faster, B is slower. A is faster, B is slower. A is faster, B is slower. A is faster, B is the same. A is faster, B is slower. So look down at A. Question A says, what pattern do you notice in the data set? Use evidence from the data to support your response. So let's look at what's expected. The pattern I see is that student A almost always, or you could say most of the kicks, or most of the time, kicked the ball into the goal faster. I noticed a student A kicked the soccer ball into the goal faster 7 of the times. Trial 1, trial 2, trial 3, trial 6, 7, 8, and 10. This one it's slower. This one it's the same. This one it's the same. And student B kicked it faster only once. The typical time for student A was 4.5 seconds. Okay, so look, the way that was figured was all of these times were added up and averaged. Okay. That probably is a good thing to figure out. So the way you would do that is 4, the way I would do it, 4 plus 4, that's 8, plus another 4, that makes 12. And then, so that's 12 including, we got that one, we got that one, and we got that one. That gets us 12. Then 4.5 and 4.5 is 9. Okay, so 12 plus 9 is 21. So I'm going to put pluses there, showing that we got those two done. Okay, and then these two makes another 9. So that gets us 30. Okay, that leaves us a 5.5 and a 4.5. So that's the same thing as 5 and 5. So that gets us 10 plus 5 more, 15. So 30 plus 15 is 45. 45 divided by 10 is 4.5. That wasn't hard. Okay, guys? Didn't require a calculator. Didn't require a lot of hard math. All right? Try to keep things simple. Showing you how we could do mental math to come up with easy answers. Oop, I'm tearing up my eraser. Darn it. All right, for student B, 6 plus 5 is 11. So we got 11 so far. 11 plus 4 is 15. So we're 15. Plus 5 more is 20. So we got those 4 answered. Those 4 in there. 20. Plus 5 more is 25. Another 5 is 30. So we're at 30. Plus 5 more is 35. Okay. So now we got 5.5 and 5.5 more. That's 11. That gets us to 46. We got 4 more. That gets us to 50. 50 plus 5 more is 55.5. 55.5 divided by 5 is 5.5. And this one was 4.5. So that's our averages. I'm going to get another eraser. Okay. It's easy because there's 10 sets and it's easy to divide by 10. 5.5. Okay. So typical time or average time for student A. Hey, that was you?
Yeah, it's got to work.
Average time for student A was 4.5 seconds, and the average time for student B was 5.5 seconds. So that's patterns that are noticed in the data sets. Okay, so the average time for student A was indeed faster than the average time for student B. Okay, so let's go back to the next question. Question B says, neither student has ever worked with this type of information before. What 3 questions might the students have about this data as they try to figure out who kicked the soccer ball with more energy? Remember, faster speed equals more energy. Okay, so what 3 questions might student A and student B have about the data sets, about the individual pieces of data, might they have when they're trying to figure out who kicked it with more energy? Okay, so here are 3 really good questions. This is going to be looking at those outlying numbers where it is. 3 really good questions. My eraser's about to fall apart. I got to get another eraser. Darn it. Okay, see this? Trial 4. 1 really good question. to B. Why did student B's soccer ball how do they word that? Number two. Who did? Get to the goal faster in trial 4, because that was an exception to that rule of in most of the trials, student A ball got there faster. Well, in that one trial, that wasn't true. That's the one where student B ball got there faster. Okay, so why'd that happen? Okay, that's one really good question. Why'd that happen that one time? Okay, that's one question. All right, another good question. Yes, I'm going to do this. Question related to that question. I'm going to put little numbers on these. Hold on just a minute, guys. Hey, I'm doing a video. What you need? I need your help making copies of this test for my students. Could you possibly come up here today? Or no? That's fine. That's absolutely fine. All right, thank you. Bye. Okay. So did student B use more energy when kicking the ball in trial 4? Okay. So that first question leads to that second question. Okay. There you go, guys. All right. How does the time needed for the ball to reach the goal relate to the amount of energy used to kick it? Okay. 3 really good questions that go right along with this data set. Okay. Part C says, let me give you this. Student A says she used more energy during the investigation than student B. Is there evidence in the data to support her claim? Let's look at this. Student A, other than trial 4, trial 5, and trial 9. Trial 5 and 9, she tied. Trial 4, was faster on with student B. The other 7 trials, student A got the ball to the goal faster than student B. Isn't that evidence that the ball had more energy when student A kicked it? Just like when Innocente ran into the desk. He brought more energy to that desk than when Allie walked into the desk, right? Because if you're moving faster, or if a ball is moving faster, it has more energy than if it's moving slower. So if this ball is making it to the net in less time, it's moving with more energy. Okay, so for 2C, the answer would be yes, since student A's soccer ball reached the goal faster than student B's ball in 7 of the 10 trials, and the average time for student A was less than the average time for student B. Student A used more energy. Student A transferred energy to the ball each time she kicked it. I'm going to assume she. It could be he. Let me show you this because I'm going to flip the page over. Okay. 2C, yes, since student A's soccer ball reached the goal faster than student B's ball in 7 of the 10 trials, and the average time for student A was less than the average time for student B, student A used more energy. Student A transferred energy to the ball each time she kicked the ball, kicked it. So she used more energy during the investigation. Guys, notice that these answers are not short. Okay. The questions aren't that long. I should have written them smaller so all the 2C could fit on one page, but oh well. Okay. And it's taking me a little while to answer them. So when my students are taking this unit assessment, it should take them a little while. Yes, since student A's soccer ball reached the goal faster than student B's ball in 7 of the 10 trials, and the average time for student A was less than the average time for student B, student A used more energy. Student A transferred energy to the ball each time she kicked it. So she used more energy during the investigation. Okay, that's your 2C. Like I said, every question has lots of parts. Okay, there's 4 questions plus a bonus question, which is just the conceptual checkpoint repeated. Okay. All right, 3. All right. Number 3. The model below shows a solar cell powering a laptop computer that is playing music. Add detailed information to the model to explain the energy transfers and energy transformations taking place. Okay. This is as close to the windmill model that we have spent since November doing as you're going to get. Okay, guys? So sun powering the solar cell powering the computer that is playing music. If you need to, underline it. Okay. Okay, this is what I have to use to go make my copies. So I have to erase it. And that's the call you heard me making a minute ago. My husband's coming. That's so he can help me make copies of this for all my little friends in a few minutes. Okay. All right, so let me go to the book copy of this. Okay. Numero. Light from the sun transfers to the solar cell. The solar cell transforms the light into electricity. The laptop transforms the electricity into light and sound. We know it's going to transform it into light, otherwise you wouldn't be able to see the laptop to play your songs. Otherwise, it's going to be random songs popping up. You're going to want to choose your songs, right? So you have to have light. Electricity transfers through the cord to the laptop. Okay, so yes, there's words, lots of them, but there's also arrows pointing from the sun to the laptop. The cord, they're showing these little, looks like lightning bolts, but it's to show that electricity, power, is going from the solar cell to the computer, and these little lines are coming out of the laptop to show sound, and these little musical notes. Okay? If you want to show something that looks like this to show me that the computer's glowing, do it to your heart's content. Okay? It'll remind me of my LED speaker. Okay? With those words and these lines to show me sound, music shows me sound. These little things right here show me there's electricity going through. These arrows show me that light is going from the sun to the solar cell. And I have to have these words. Light from the sun transfers to the solar cell. The solar cell transforms light into electricity. Electricity transfers from the cord, through the cord to the laptop. And if you want to get more specific, electricity transfers through the cord from the solar cell to the laptop. It's not going to Bluetooth to the laptop. Okay. The solar cell has to physically be attached by a wire to the laptop. So you could say electricity transfers through the wire to the laptop. Electricity transfers through the cord to the laptop. Some way you've got to show me the electricity is running through a wire or a cord to the laptop. And then you're going to tell me the laptop transforms the electricity into light and sound. Okay, that's the answer I need for 3. Okay, Number 4. Go back to the original question. A blue marble is sitting on a flat surface when a white marble collides with it. Describe what happens to the energy of each marble. So you're going to have to tell me what happens to each marble's energy before, during, and after the collision. If it helps you, you can think of pool table, the balls in the pool table. Or you can think of marbles. So you have 2 balls. A blue marble sitting still. A white marble is rolling and hits it. Describe what happens to the energy of each marble before, during, and after the collision. If needed, you can make a drawing to help organize your thoughts before the collision, during the collision, and after the collision. Okay. So they didn't actually draw a drawing here. I'm going to do a drawing for my sake. And I'm going to turn it sideways. Before collision. Let me get my blue colored pencil. Blue. Of course, I grabbed the purple because, you know, dictates I'm going to grab the wrong one. And blue. So the white is rolling. Moving. Before collision, during collision, after collision. I'm out of space up here at the top. So we're going to hear a sound as they collide. Then, actually I need to show it. My eraser just broke completely. Show the white one over here and the blue one over here, because it's going to make the blue one roll away. Okay, so once the white one hits it, it transfers its energy to the blue marble, right? And this one's going to stop, right? So the blue marble will have the energy it'll hit during the collision. Oh, I want to wear this. So when these hit, there'll be, I don't know how to show this, I guess like this. 2 marbles collide, creating some heat. Now, obviously, they're not going to create a lot of heat. There it goes. But we talked about wreck, like a car wreck, that creates a good bit of heat. Our little toy cars, they're not big enough to create very much heat, but in an actual car wreck, people actually get burns because they're bigger, they involve more friction, faster speeds, bigger vehicles, more weight, more mass. So it's going to create a lot more heat. There's going to be a lot more energy involved. So there's going to be more heat created. Okay. So the drawing is not what I'm looking for per se. I'm looking for the words. Okay. So the words. The blue marble doesn't have any energy of motion because it is sitting still before the collision. The white marble has energy because it is moving. It is also making a sound as it rolls. Okay, so think about it being on a floor or a table. Marble's gonna make sound as it rolls. It just is. It's glass. It makes sound. Right? Think about it rolling across the surface. It makes sound. Okay, so some of its energy, sound as it rolls. And this thing here is stopped. So I'm going to put on here sitting still. Please remember, if you want to draw these, fabulous. Label them, even better. But what I'm grading are all these words. Okay. During the collision, the white marble hits the blue marble. We know some of the white marble's motion energy is transformed. You got to use the word transformed because we hear a sound and both marbles get a little warm. So that's that heat. Some of the white marble's motion energy is transferred to the blue marble, causing it to move. So this explanation mentions transformation into sound. So it talks about motion energy, transform, sound. And then it says some of it goes to heat. Then it talks about transferring some of the motion energy to the blue marble. Okay. That's a lot of information it's given me. And I need to see all that for the correct answer for full points. You guys know how picky I am with grading. The reason I'm picky is I'm trying to get you prepared for your LEAP test. Okay. The LEAP scorers are just as picky as me, if not more picky. Okay, guys? These tests are hard. It's not me that makes it hard. I'm trying to grade it just like the LEAP scorers. I just talked to the 5th grade science teacher about it, Miss Smith. She said the same thing. These tests are hard because there's so much critical thinking involved. All right, I need to see. White marble, you could say hits or collides with the blue marble. Some of the white marble's motion energy is transformed because we hear sound. Both marbles get a little warm, or both marbles create some heat. Some of the white marble's motion energy is transferred to the blue marble, causing it to move. Okay. After the collision, the blue marble starts moving because the force from the collision transferred motion energy to it. The white marble's motion changes and it eventually stops. Okay, guys? Not particularly long, but there's a lot of information in there, guys. Okay. Then your bonus question is going to be that conceptual checkpoint that I went over at the beginning of this video repeated. All right, guys, you good? All right. So I'm going to go downstairs and make copies of your end of module assessment and your conceptual checkpoint that I'm going to type up for your bonus question. All right, guys. And your end of module assessment will be Thursday. We will go back over this again tomorrow in class, and your conceptual checkpoint will be tomorrow in class. Tomorrow's lesson will be short because we're going to be going over this assessment.